everyone, welcome back to our channel NCERT Science. So this video is a continuation of our NCERT Science series, and today we will be talking about another physics chapter, chapter 11, work and energy. Alright, so in the previous chapter we finished gravitation, and the next chapter is going to be sound. So I believe that sound would be the last chapter in physics, and then we will switch over to 3 more chapters of biology. Alright, so before we start, I want to do my standard speech. Alright, so first point is that I want to mention that these videos will be helpful to those preparing for CBSE exams, NTSE, NEET and JEE. Alright, and second thing is that I want you to take your own notes, because I will be presenting in my own words, and I have pictures taken from the NCERT Science textbook that I found online on NCERT's official website. And just because I am explaining in my own words, it doesn't mean you can copy my words, right? So I want you to take your notes in your own words, because it will help you remember better during your exam. Alright, and then the third thing is that I want to make sure that these videos will be helpful to everyone, whether they're and especially if you're preparing for the exam that's approaching very shortly, like the day before your exam is also approaching, and you want to revise the chapter. I want these videos to be helpful to such people as well. So I'm quickly going over the topics, and if you think I'm going fast, feel free to change your YouTube settings to 0.75 speed. Alright. So, chapter 11, we are talking about work and energy. Alright, so this is, as I said, this is a physics chapter, and this is a pretty important basic chapter. Alright, this will help you in your 11th, 10th, 11th, and 12th as well. Alright, so work and energy. Alright, so all this is introduction again, like always. Alright, so we start with a question: what is work? So when you say, when you're talking to your friends, you say, I worked a lot yesterday, I finished chapters 9 and 10 in NCERT Science, I just did so much, I got so much done, I feel like I worked a lot yesterday, I was very productive and all of that. But is it really considered work? That is what we are going to learn now. Alright, so there's a difference in what we in the way we use the term work in day-to-day life and the way we use it in science. So if you say I'm going to work, and you go to your office and you sit in front of the computer or something for 8 hours a day, and then you come back home and you say I worked a lot today, that is not work. Alright, even you working on your weak areas is not work. Alright, it's not scientifically considered work. Alright, so if that is not considered work, what is considered work? Right, so if you're preparing for an exam, you sit and study, you take your own notes, you draw, you make flowcharts to remember better, you talk to your friends, you talk to your teachers, you clarify doubts, you watch videos, YouTube videos, any other explanatory videos, all of that, and then you say at the end of the day, you're like, oh, I worked hard, it's time to get a good night's sleep or something like that. But that's very little work if we go by the scientific definition of work. Alright, so in contrast to studying the whole day, let's say you're working hard to push a huge rock. Alright, and you're doing that the whole day. The rock does not move at all despite all the effort. Alright, it's a very huge rock. You're not able to move it at all, but you're still standing there throughout the day, and you're working throughout the day, but that does not work either. Alright, you're completely tired, you are out of energy, but that doesn't matter. You did not, according to science, you did not work. Alright, so another example, there are many other examples here that I want you to read because it's fun, and it is fun to read an example and think, oh, this is definitely work, and then at the end of the paragraph they say this is not work either. It's very fun. All right, so to understand what exactly is work in science, we have an activity, and then we have this scientific conception of work. Alright, so when do we scientifically agree that you have worked? To understand the way we work and define work from the point of view of science, let us consider some situations. Alright, so these are a few more situations. Alright, so that I want you to read, and pause the video here, read through the text, and hit play again once you're done. So when I start explaining again, you will know what I'm talking about. Alright, so we have another activity down there, that is 11.2, and 11.3 is up here. All these you can do. They're all thinking activities. Alright, so how is work defined in science? To understand this, we shall first consider the case when the force is acting in the direction of displacement. Alright, so if you read all these examples, you will see that all of them had one common thing, that the object was moving in the direction of the applied force. All right. So to define work scientifically, let us consider a situation in which a particular force is acting in the direction of displacement of that object. All right. So let's say this is a brick. I'm guessing this is a brick because it looks like a brick. All right. So this is a brick or a box or a lunch box, whatever it looks like to you. I'm going to go with brick. All right. So the brick is here, and then you push the brick. All right. You're just sitting there, completely relaxed, comfortable, and the brick is also not very heavy. You push it forward. All right. If this is you're sitting here, and you push the brick forward, it moves forward by a distance s. All right. So we define work to be equal to the product of the force and displacement. All right. So when you push the brick here, you exerted x force, let's say, and that brick moved by s distance. So work done would essentially be xs. Alright, because work is force times displacement, and force is x, displacement is s, so work done is xs. Alright, so x amount of force multiplied by s length of displacement would give you the work done. Alright, so now work done by a force acting on an object is equal to the magnitude of force multiplied by the distance moved in the direction of the force. Alright, so work is only magnitude, it does not have any direction. Alright, so if force is 1 Newton and displacement is 1 meter, then the work done is 1 Newton meter. Alright, so the unit of work is Newton meter or joule, joule. I've heard many people saying multiple versions of this. I'm going to stick with joule, and I apologize to those of you who have been accustomed to hearing joule. I hope you don't cringe. One moment. Alright, I just googled to see how it's pronounced. Apparently it's joule, so I'm going to say joule. Alright, now I'm apologizing to those of you who got accustomed to hearing it as joule. Alright, so it's joule. Google told me that, so I'm going to go with that. Alright, so 1 joule will be the work that is done when an object moves 1 meter in the direction of the force applied as a result of a force of 1 Newton. Alright, That's a very easy and simple way of saying it. 1 joule is the work done when an object moves 1 meter in the direction of applied force under the influence of a force of 1 Newton. Alright? So you might have noticed that I repeated the statement twice, and both the times I said it in a different way. That is because I didn't memorize anything. I'm just making a sentence out of whatever makes sense to me. Alright? Similarly, I want you to write down in your notes whatever makes sense to you as long as it is correct. Alright? So what is the work done when the force on the object is 0? And what will be the work done when the displacement of the object is 0? Refer to the conditions that are to be satisfied to say that work is done. So, if work is force times displacement, if force is 0, work will be 0. Alright? So, let me elaborate it. If force is equal to 0, work done is 0 times S, work done is 0. Alright? If displacement is equal to 0, work is equal to force times 0, work is equal to 0. Joule. Alright? So, if you refer back to the situations that we read in the beginning, you will know the reasons behind us saying that such situations are not considered work. Because in the first set of situations, we saw that there was no force being applied. You were just sitting there doing your work, you were sitting there studying, you were sitting there and doing your office work or whatever, right? There was no force, the force was 0, the work is 0 joules, alright? And in the second set of situations, displacement was 0. You were moving a very heavy rock. I understand you might have, you probably felt very tired and you were probably very sweaty, but it doesn't matter because the displacement was 0, and according to the scientific definition of of work done, if displacement is 0, then the work done is 0 joules. Alright? So that is why I said that all those situations were not considered to be work done. So when is work done and when can we say that work is done? Alright, so in order to be able to say that work is done, two conditions need to be satisfied. The first one is that there needs to be a force applied, and the second one is that the object must move in the direction of the applied force. Alright, so in order to say that work is done, there should be a force that is applied, and the object should move in the direction of the force that is applied. Alright, so it's and both of them should satisfy. Alright, there is no point in the object just moving without you applying force. There is no point in you applying force without the object moving. In both the cases, work done would be 0 joules because both the situations need to be equally satisfied. Alright, we have one example, a numerical here, and a question that I want you to try on your own. I want you to try both of them on your own. If you have a question about any of either of the problems, feel free to go back to that part of the video where I explained it. Alright, so consider another situation in which the force and displacement are in the same direction. Alright, a baby pulling a toy car parallel to the ground, as shown. The baby has exerted a force in the direction of the displacement of the car. In this situation, the work done will be equal to the product of the force and displacement, right? So, because work is force times displacement. Alright, in such situation, work done by the force is taken as positive. Alright, and then that would be the first situation. Second situation would be a situation in which an object moving with uniform velocity along a particular direction is now under the influence of a retarding force F that is applied in the opposite direction. Alright, so the angle between the two directions is 180 degrees. Let the object stop after a displacement S. In such a situation, work done is negative because either the force or the displacement is negative. Alright, in the third situation, Also, one to summarize the second situation in one statement, it would be the two situations, it would be work done is negative when the force acts opposite to the direction of displacement. The second one would be work done is positive when the force is in the direction of displacement. Alright, and then we have a third situation that has not been mentioned here as far as I can see. So I'm going to take you on a plain screen and I'll explain the three situations. Alright, so the first situation is positive work. Alright, and so what are the conditions to be for a work to be considered positive? First one is a standard standard point, right? So work has to, force has to be applied. Alright, the second one, let me do it in the form of a table. That's gonna help you remember it better. Okay, so let's draw a table here. Yep, that's what I want. Alright, no, not what I want. Okay, so this would be positive work. That's the first situation. This would be negative work. And if there is a positive and a negative, what would be the third kind of the third type? Zero work. Alright, so for zero work, I do not know why that's happening. Don't want it to do that. Alright, never mind. Okay. My apologies. I had to change the settings because it wouldn't let me do what I want to do. Alright, so positive work, negative work, and zero work. Alright, so this is like a rough table. I think the roughest I've ever done on screen. Alright, so that is that. So the first one is common for all three. That would be a certain force has to be applied. Alright, let the first point be force has to be applied. Alright, and that goes on to the first two. Alright, the second one would be for just positive work. It would be for displacement must occur in the direction of applied force. Alright, here displacement is opposite, I'm using abbreviations, to applied force. Alright, and let's just not talk about zero work yet because I think that's in 10th grade. So let's not go to 10th grade yet. Alright, I just remembered that it's probably in 10th grade. Okay, so the first point is that work has to be applied. It is common for both positive and negative work. The second point is that displacement must occur in the direction of applied force. Only then will work be considered positive. Alright, that's point number one, point number two. And a simple way of remembering the difference between the two would be to talk about theta. Let theta be the angle between applied force and displacement. Alright. So if theta is the angle between applied force and displacement, theta should be 0 degrees. And theta should be 180 degrees for this. Alright. So 0 degrees would mean that if work is being done in this direction, displacement is also in this direction. However, if you're talking about theta of 180 degrees, so if you have work and displacement along the same line, do work with red and displacement with blue, so that the angle between them is 0. Alright, it's 0. However, if you consider work being done towards the right and displacement towards the left, the angle between work done and displacement is 180 degrees, right? So this is an easy way of remembering that if theta is equal to 0 degrees, the work done is positive, and if it is 180 degrees, work done is negative. Alright, so that is a very important and easy way to remember the difference between positive and negative work, because whenever, and I expect you, if you were listening carefully and if you understood properly, I expect you to be able to think whenever you hear a situation of work throughout this course, throughout this lesson, throughout this course. I want you to think, I want you to automatically think whether it's positive work or negative work, and if and after a while you shouldn't even be able to think. It should automatically come to you, and whenever you hear a situation about work, you should automatically go, oh, that's an example of positive work, or oh, that's an example of negative work. Alright, and that will show your success in this course. Alright, moving on. We have activity. We have an activity 11.4. Alright, and on. So I didn't elaborate on zero work because it's not given in your textbook and I didn't want to confuse you. But zero work is done if the angle between the force and displacement is 90 degrees. That's something that you can keep in mind, something that will help NTSE, NEET and JEE students. Alright, so we have 4 questions here. 1, 2, 3, 4 that I want you to try on your own. And let's talk about energy. So we finished talking about work. Now we'll start talking about energy. Alright. So energy is required for everything. Alright. Life is impossible without energy. The demand for energy is always increasing. Alright. So where do we get the energy from? The sun is the biggest natural source of energy to us. Its energy is never going to deplete, not in a very, very long time. Alright. So many of our energy sources are derived from the sun. Very few are derived directly from the sun through solar energy. I'm going ahead of myself right now, but I just want to make it clear that when they mean derived from the sun, they mean directly and indirectly. Alright. So I want you to list a few sources of energy. Pause the video, list them, and once you're done, play this video again. Alright. So in science, energy also has a definite meaning. Alright. So think of all the sources of energy that you're able to think of right now. List them, and once you're done, let's move on. Alright. So energy, an object possesses energy. An object that possesses energy can exert a force on another object. Alright. So when this object exerts a force on the other object, energy is transferred from the first object to the second object, or the former to the latter object. Alright. So the second object may move as it receives energy and therefore do some work. But it may move. It's not always the case. Alright. It's most of the time whenever we think of energy, we think of the ability to move. Alright, so energy possessed by an object is measured in terms of its capacity of doing work. Alright, and the unit of energy is the same as the unit of work, which is joule. And 1 joule is the energy required to do 1 joule of work. Alright, so a larger unit of energy, which also happens to be a larger unit of work, is called kilojoule, and 1 kilojoule is equal to 1000 joules. Alright, this is an important relation that you should know because that will help you solve your numericals. That is going too far. Alright, so let's talk about the forms of energy. So how do you know that some entity is a form of energy? Think it over and discuss it with your friends or your teachers or your parents. Alright, so we're talking about kinetic energy now. We have two activities that you can try. Alright, and once you try them, let's move on. Alright, so moving object can do work. An object moving faster can do more work than an identical object moving relatively slow. Alright, so a moving bullet, blowing wind, a rotating wheel, a speeding stone, they all can do work because they have a force that has been applied on them and they are able to move. They are moving in the direction of the force applied. So how does the wind move the blades of a windmill? Objects in motion possess energy, and this energy that moving objects possess is called kinetic energy. Alright, so previously in this video, very recently, I said that objects may or may not move when they're given energy. But then later, there was a statement in the textbook that said energy, the unit of energy measures how much work that that object did. So you might be wondering if you said, so you might ask me, you just said that objects may or may not do work. Or they may or may not move if they're given energy. So how come we're measuring energy for those objects which don't move? In such cases, we will use the energy that is stored in them. Alright, and we'll talk more about that when we, and that is called potential energy. Alright, so we'll talk more about that when we reach that part of the lesson. So just as how potential energy is the energy that is stored in objects, kinetic energy is the energy that is that helps movement in moving objects. Alright, so kinetic energy is possessed by everyone. All of every moving body. Alright, so whether it is a player or any sportsman or an actor, a dancer, right? Even me, I am writing on this screen and I'm moving. So I have kinetic energy in my hand maybe. And when I'm talking, I'm moving around my hands. Even though you can't see me, I'm moving around my hands. I don't know why, but my hands have kinetic energy. Alright? So how much energy is possessed by a moving body by virtue of its motion? By definition, we say that the kinetic energy of a body moving with certain velocity is equal to the work done on it to make it acquire that velocity. Alright, so when we think of that, when we think of kinetic energy as a function of its velocity, we can use this equation of motion, v square minus u square equals 2as. So we can make displacement the subject, and making a quantity a subject essentially means isolating it, making it alone on one side of the equal to sign. Alright, so S is equal to v square minus u square by 2a, because this 2a went on to divide on the left side. Alright, so force is equal to mass into acceleration that we learned in chapter 9, right? And here we saw that acceleration, velocity. So you can write it as ma times v square minus u square by 2a. Alright, that would give you mas. Alright, So force can be written as ma into v square minus u square by 2a, or if you take if you cancel the a's here, it will be half m v square minus u square. Alright, and if an object is starting with an initial velocity of 0, there is no point in having this u square here, right? So that is when this w equals half mv square comes in. This is a very important, commonly tested equation that you need to remember. It's not very hard either, it's really easy. Kinetic energy is half mv square. Alright, so this is the important formula. Energy is kinetic energy, so it's E sub k, that is, you can also write it as ke, kinetic energy, equals half mv square. Alright, now you have a few numericals, you have a couple of them, and then you have 3 questions that I want you to try on your own. And now we're talking about potential energy, that is the energy that is stored in objects that I was talking to you about previously. We have 3 activities here. No, I think it's 4, which is awesome, because I expected 2. Yep, there are 4. Alright, so try to go through all of them, and if you can do them, pause the video and do them. And once you're done, play the video and let's start talking about potential energy. So in all of these situations, the energy gets stored due to the work done on the object. Alright, so the energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. So if an object is being transferred energy, and if that object is not moving, then the energy that has been transferred to the unmoving object is stored as potential energy in itself. Alright, so when you stretch a rubber band, you're transferring energy to the rubber band, and the energy is transferred to the rubber band as its potential energy. Alright, when you wind an alarm clock, you are transferring energy to the coil inside that, to the spring inside the alarm clock, and that energy is being stored as potential energy, and throughout the night it will that potential energy is slowly going to get transferred into kinetic energy, and that is what causes the arms of your clock to move throughout the night, even though you don't have to sit and wind the key yourself. Throughout the night you are giving the spring potential energy, and the potential energy is gradually being transferred into kinetic energy, which will help move the arms of the clock throughout the night. Alright, and that's the same with an arrow and a stretched bow. Alright, and potential energy of an object at a height, this is an important concept. So an object increases its energy when raised to a height. Alright, so this is because work is done on it against gravity while it is being raised, and the energy present in such an object is the gravitational potential energy. Alright, so the gravitational potential energy of an object at a point above the ground is defined as the work done in raising it from the ground to that point against gravity. So if it's at a height h, the work done to move this object a, h meters, or h, I'm just assuming the units are meters, h meters above the ground is the gravitational potential energy that is present in object A, h meters above the ground. Alright, so it is easy to arrive at an expression for gravitational potential energy of an object at a height. So when we consider an object of mass m, alright, and the height h, from the ground, a force needs to do this, right? So the minimum force that is required to raise the object is equal to the weight of the object, and the weight of the object is mg. G is the acceleration due to gravity. Alright, so the object gains energy, and that energy is equal to the work done on it. So let the work done on the object against gravity be W. Alright, so for work done, that is W. W is force into displacement. Force is mg So since work done on the object is equal to mgh and energy equal to mgh units is gained by the object, the potential energy E sub P or PE, potential energy, equals mgh, which is essentially the product of the mass of the object and the height at which it is raised along that is multiplied by the acceleration due to gravity, which happens to be 9.8 meters per second square. That is a constant value for G. Alright, so it is useful to note that the work done by gravity depends on the difference in vertical heights of the initial and final position, and it's not it doesn't depend on the path taken by the object. So if this is point A, this is point B. No, I did wrong. If this is point A and this is point B, it doesn't matter whether the object moves this on a straight line, that's not straight, but let's assume that's straight, or whether it moves like that, or whether it moves like this. Alright, it doesn't depend on anything. It doesn't depend on the path. It doesn't depend whether the object travel like that, although it's highly unlikely for the object to travel like that. I'm just showing you different various ways that the object can travel from one point to another, and I'm trying to tell you that the path taken by the object is not at all concerned when you're finding the potential energy. It's just the height. It's like the end, the conclusion is that the height is what really matters at the end. Alright, so it doesn't depend on what path you took, it just depends on the height. Alright, so that's something to remember. And there are two examples here, and then we talk about whether various energy forms are interconvertible. So can we convert energy from one form to another? Think about it. Pause this video and think about it. Can you transfer energy from one form to another? Alright, so I want you to think about water. So water being stored in a dam, and then that water being released from a height onto a turbine, and that turbine turning to produce electricity. Alright, so did we change from one form to another form of energy? Yes, we did, because we converted hydro energy present in water, into electrical energy, right? Similarly, a plant took solar energy and it produced food. That is chemical energy, right? It transferred solar energy into chemical energy to make food, right? So all of that is conversion of energy from one form to another. And if you remember the law of conservation of energy, we know that energy can neither be created nor destroyed. It can only be transferred from one form to another, right? So that clearly shows us that energy can be converted. Alright. Now there are two activities that you can try, and then we have the law of conservation of energy that I was just talking to you about. Alright. So in the two activities, the latest activities that you did, you might have seen that one form of energy can be changed to another form, right? So what happens to the total energy of the system during or after that process? Whenever energy gets transformed, the total energy remains unchanged. Alright, so that is the law of conservation of energy. So according to this law, energy can only be converted from one form to another. It can neither be created nor destroyed. Alright, not or, neither, nor, either, or. Alright, English lessons, we get English lessons as well. Okay, so the total energy before and after the transformation remains the same. The law of conservation of energy is valid in all situations and for all kinds of transformations. So there is no exception for the law of conservation of energy. Energy can never be created, it can never be destroyed. It can only be converted from one form to another form. That's it. Alright. an example here. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy is mgh and the kinetic energy is 0. Alright. So why is it so? First, let's talk about this statement in two halves. Alright. In halves. Alright. So the potential energy is mgh is one part. Kinetic energy is 0 is the other part. So an object is made to fall freely from a height h. At that point h, the object is not moving, right? So it has potential energy. And what is the formula for potential energy? mgh. That is why we took potential energy as mgh. Why is the kinetic energy 0? Because I just said that the object is not moving. So if the object is not moving, obviously its kinetic energy is 0, right? That is why the potential energy of this object is mgh and the kinetic energy is 0. Alright. So why is this kinetic energy 0? It is 0 because the velocity is 0. Why is the velocity 0? Because it's not moving at all. Right. So the total energy of the object is mgh. Alright. So when I was in 9th grade, when I was doing NCERT 9, my teacher did this cool diagram that helped. I can still remember the diagram. Not sure if I ever did it again, but let's just assume that all this is just one ball. There's just 3 instances in time. Alright, A, B, C. This is the ground. Alright, the whole height is h. Alright, so if the complete height is h, and if this is x, what is this? Think about it. This is h and this is x. What is this? H minus x, right? So AC is h, AB is x, BC is h minus x. So at point A, let's say at A, potential energy is m. So the mass of this object is m. At all 3 instances it is m because it's the same object. Potential energy is mgh. That is equation 1. Kinetic energy is half mv squared and v square is 0. So kinetic energy implies kinetic energy is 0. Alright, this is equation 2. So at A, potential energy plus kinetic energy is mgh plus 0, which happens to be mgh. Right? Alright. So that is at A. Alright. Now let me zoom out a little bit here because I need space. Alright. So at B, potential energy is mg. The formula for potential energy is mgh. And at this point, h is h minus x. Alright. So mg h minus x. That is potential energy equation 1. Kinetic energy is half mv squared, right? And how do you find the velocity here? Think about the equation of motion. V squared is v squared minus u squared equals 2as, right? So u squared is 0. V square is equal to 2gh because a is g and s is h minus x. Alright, so half m and this is 2gx minus h. That will be 2 and 2 get cancelled. Kinetic energy equals mg h minus x. Alright. Then, if you add them up, potential energy plus kinetic energy will be mgh. Alright. And now, at C, potential energy is equal to mgh and h is 0. So, potential energy is 0. That will be equation 1. Kinetic energy equals mg half mv square, alright, and v square is 2gh, alright. So half m 2gh, that will be mgh, alright. So I just realized this is mgx because the distance is x there, right? Not mgh minus x, this is x. Sorry about that. Because at B the height is x, right? So it's mgx, this is h minus x, so adding them up would give you mgh, alright. And then we have mgh here, but that is kinetic energy, that would be colors, that would be equation 2. So potential energy plus kinetic energy is equal to 0 plus mgh, which is mgh, alright. So if let me zoom out a little more. Okay. Okay. So if you look at it at once, if you look at the whole thing at once, right? And if you consider this to be equation A, this to be equation B, this to be equation C, you will see that A equals B equals C. Alright? Okay. Alright? A equals B equals C, which shows that energy is constant at every point. Alright, this is a very important question, theory question. Alright, sometimes you even get questions about this in NTSE, where they ask you, they label this diagram here or some similar diagram, and they say what's happening at this point, what's happening at that point. Alright, so essentially potential energy plus kinetic energy is always constant. Alright, so the sum of potential energy and kinetic energy is its total mechanical energy, and that's why mechanical energy, we can conclude that mechanical energy is equal at every point. Alright, so during the free fall of an object, the decrease in potential energy at any point in its path appears as an equal amount of increase in kinetic energy. Alright, so there is a continual transformation of gravitational potential energy into kinetic energy. So at point A, if you go back to the diagram and refer it, at point A, there was no kinetic energy, there was only potential energy, and that potential energy is gravitational potential energy, alright, because it's at a height. And at point B, potential energy decreased, gravitational potential energy decreased, and kinetic energy increased. So what happened? The energy was transferred, a little energy was transferred from the gravitational potential energy to kinetic energy. And at point C, there was no potential energy, but there was completely kinetic energy. So what happened then? Completely potential energy transferred its complete energy to kinetic energy. That's how potential energy became 0 and kinetic energy was maximum. Alright, so continuously, potential energy or gravitational potential energy was transforming its energy to kinetic energy. Alright, so you have an activity here that seems very fun. Alright, so rate of doing work. Let's talk about the rate of doing work. Do all of us work at the same rate? Answer is no. Do machines consume or transfer energy at the same rate? Answer is no. So there might be machines that consume energy faster than others or slower than others, and most of the time we prefer faster machines, right? And all of us do not work at the same rate because there is an average. Even if you're talking about schools, there is an average pace, right? So they don't change the study plan. Teachers don't change their study plan based on an individual student, whether that student is able to do is able to grasp the material faster or slower. It doesn't matter, because if um, and because of that, the teachers tend to take an average pace and they plan their lessons accordingly. So all of us do not work at the same rate, and machines do not consume or transfer energy at the same rate. Alright, so agents that transfer energy do work at different rates. So it's the agents that transfer energy that do work at different rates, which causes a change in the rate of work done by different objects. Alright, so there is an activity that will help you understand the statement better. Alright, and then we reach a conclusion that just as how a stronger person may do a certain work in a relatively less time, a more powerful vehicle would complete a journey in a shorter time than a less powerful one, right? So when we say it's powerful, we talk about when we're talking about machines like motorbikes or motor cars, and we say, oh, it's a very powerful car. We're talking about the rate at which it is doing work. Alright, so power measures the speed of work done. Alright, so how fast or slow work is done, that is power. So power is defined as the rate of doing work or the rate of transfer of energy. Alright, so I mentioned in the previous videos, in one of the previous videos, that we never say rate of doing something per time. If we want to mention rate of, we eliminate the time. And if we want to mention per time, do not use rate of. Alright. So here they said how power is defined as the rate of doing work or the rate of transfer of energy. Alright. So in case you didn't understand what I was talking about the rate done and per time, go back to our previous videos and watch it, because then you will get this sense of completing all the videos, right? Because whoever has been with me since the beginning, they know all my jokes. They know whatever I'm talking about when I refer to a previous video. Those of you who joined me recently or just for this video, welcome to my channel, but also go back to the previous videos and watch it, because we have our own inside jokes, and I just came up with this in the previous video, and I'm going to be saying it in the rest of the videos as well, if I remember. Terms and conditions apply, if I remember. Alright, so power is work by time, and the unit of power is watt. What is the unit of power? It's watt. Alright, so watt is in honor of James Watt, and it has a capital W symbol. So weight, work, and watt are all capital W. So you just need to go by whatever one based on the context. Alright, so essentially power is work done by time, and work done is joule. Time is second. So the unit of power could be joule per second, but it is also watt. Alright, 1 kilo. So they gave important relations here. 1 kilowatt is 100 watts, or 1000 watts, or 1000 joules per second. Alright, so the power of an agent may vary with time. If you have an old refrigerator, you might know this, right? The power of that refrigerator when it was new is not as much as when its power now. That is because the power of an agent may vary with time. It might not be the situation for every old refrigerator, but most of the time this is what happens, right? So this means that the agent may be doing work at different rates at different intervals of time. And that is why the concept of average power is useful. Alright, so we obtain average power by dividing the total energy consumed by the total time taken. Alright, that is average power. And then we have a couple of numericals here and 4 questions that I want you to try on your own. And we are talking about commercial unit of energy now. So joule is too small to express large quantities, so it's inconvenient. So we use a larger quantity of energy called kilowatt hour. So what's kilowatt hour? So let's say we have a machine that uses 1000 joule of energy every second. If this machine is used continuously for 1 hour, it will consume 1 kilowatt hour of energy. So 1 kilowatt hour is used in 1 hour at the rate of 1000 joule per second. Alright, so 1000 joule per second is 1 kilowatt, because 1 joule per second is 1 watt. 1000 joule per second is 1 kilowatt. Alright, so if you take, that looks like P, I meant 1000. Alright, so if you take 60 minutes, right, that is 1 hour. So 1 kilowatt hour, that is 1 kilowatt for every hour. So kilowatt hour is a larger unit of measuring energy. Alright, so the energy essentially here is 1 kilowatt hour, which is 1000 watts, because 1 kilowatt is 1000 watts, and 1 hour is 3600 seconds. So that's like 36 lakhs joules. Alright, so that's 3.6 into 10 to the power 6 joule. So 1 kilowatt hour is 3.6 into 10 to the power 6 joule. Alright, and I want to mention that kilowatt hour, it may look like I'm over here, it may look like the W is lowercase, but it's not. Kilo, K, and H are lowercase letters. The W is an uppercase letter. Alright, because watt is in honor of a scientist, and that needs to be in capital letters. Alright, so we have a few more numericals. Turns out it's just one. I expected more. And then we have another activity here. Alright, and with that, we are done with the lesson. Just like that. This was a very short lesson. It's very sweet, but it's also very important. Alright, so we have what you have learned points here. That they just sum up the lesson very quickly. You can read them the day before your exam or the day of your exam to get a basic recap of whatever was explained in the video. Then we have exercises that I recommend you try after you are confident that you know the entire chapter very well. Alright, and it's time for my points to recap. Alright, if I can zoom out, I would like to. Okay, cool. So we started with introduction. We looked at many situations. We talked about whether a certain situation is considered work or not. We talked about 2 sets of situations, one in which force was 0, one in which displacement was 0. And then we said that all these situations are not considered work because the scientific definition of work is that in a situation work is said to be done if there is a force that is applied on an object and if that object moves in the direction of the applied force. Alright, so then we talked about work. When we talked about positive and negative work, I just gave a quick point about zero work. I also had a hard time doing the table to differentiate between positive and negative work, but that's alright. And we talked about energy. We talked about potential and kinetic energy. We talked about the forms of energy. Alright, and we talked about converting between energy forms, let's say. Alright, and then we talked about kinetic energy first. Kinetic energy, and then we talked about potential energy. We talked about the law of conservation of energy. And then I don't know why these. We talked about power and the commercial unit of power. So power is the rate at which work is done, and the speed. It measures the speed of the work being done. So that's work done per unit time, and the commercial unit of power is kilowatt hour, with the W being an uppercase letter. Then we did the exercises. I scrolled over the exercises page, and I asked you to do the exercises only once you were familiar with the concepts. Alright, so with that we end our lesson. Yay us, we can do this. It's a very nice and short lesson. It has many important points, but it's very easy to grasp. Most of it we already learned previously. So this is a very nice and short and sweet lesson. Alright, so I hope this video helped you, and I hope it helped you understand the concept a little better. And head on to the next video, which will cover chapter 12, which is also a physics chapter that covers sound. Sound is a very important chapter. It's going to be carried forward into year 10, 11, 12 as well. So it is an important chapter. Make sure you head on to that video after this, and make sure you understand the concept better. If you face any difficulty understanding it at school or some institution, I hope I helped you. And just don't forget that you can do this. Alright, have a great rest of your day. Do not forget to like and share this video, subscribe to our channel for more content, and all the very best for your exam. You can do this. Bye bye.